Problem 1631, path with minimum effort. So the premise is that you are a hiker starting at 0, 0 and you want to make it to the bottom right corner. But you want to take the path with the least effort, and the amount of effort in a route is defined as the maximum absolute difference in heights between two consecutive cells. So in this route right here, differences from 1 to 3 is 2, 3 to 5 is 2, 5 to 3 is 2, 3 to 5 is 2. So the max of all of this is equal to 2, so that's going to be our effort. So how do we go about doing this problem? Well, the idea is simple. We want to create an algorithm that can basically tell us what is the minimum effort needed to basically get to like this node, for example. In that case, we're just going to use a heap. And every entry in the heap is just going to basically represent a route it took to get to this position. And we're going to store the effort here and the node that the effort took to get to this node in the second position. So to simulate this idea, let's use a less complicated example. 1, 2, 3, 8, right? So initially the heap is going to store the starting node, right? And how much effort did it take to get to this node? Well, we start at it, so it's 0, and the node is 0, 0. It's the position. So the reason why we store positions is because now we can go to either one of these values. And again, there's 4 cardinal directions, so having this coordinate here is going to be helpful to get to these coordinates. So 0, 0, we can now, let's say, go here. So now we're going to pop this out, and we're going to append 2, or rather 0, 1, right? But how much effort did it take to get to this point? Well, it's going to be the difference. The max difference between the current difference with the difference here. So that's going to be obviously 1. And we're going to also push here, push this node, because we can reach this node from 1. So that's going to be node 3. So node 3 is 1, 0, and the effort it took is going to be 2. So heap stores the minimum element first, so 1 is at the top. So we're going to now look at 2. When we look at 2, we're going to pop this from the heap. And we can go down, right? And when we go down, it's going to be the max between 1 and 6. So that's going to give us 6. So here, we're going to get 6. We're going to get 6, 6, 1, 1. But we push this back into the heap. And notice, because 6 is larger than the effort of 2, it's going to go behind it. So it's not going to immediately return our answer, right? Because we want the minimum effort. So now 2 is finished traversed. Let's get 3. So we pop this from the heap, and we can reach the last node, which is 8. So that's going to be 1, 1. But how much effort did it take? Well, it's going to be the max between the effort of this path here, which is going to be the current value here, so 2, and the new traversal distance of 5. So that gives 5. Now 5 is less than 6. So the top element in our heap is going to be the path with the least effort. So when we pop this, we realize 1, 1 is our final destination. So we should return the value of 5 from the solution. And with that, we can program this up in Python. So as we said, we're going to be traversing this BFS style. And we're going to need a heap to basically store the min path to that node at the current moment. So import heap q. So we're going to have a heap like so. And what's going to be in the heap initially? Well, it's going to be the point 0, 0. So basically what this is storing is it's going to be the effort, comma, xy position of the current node, right? The effort it took to get to this node. And with that, what else can we do? We have to have a visited set, right? Because it doesn't make sense to basically go to one node and then go back, right? It's going to increase the effort. It's just not going to add to the result. So visit every node once. So visit is set here. And with that, we can just start iterating BFS. So while the heap is not empty, it means there's values to traverse to. So the effort and the x and the chords, right, is equal to heap q dot heap pop from heap. And the xy of our chords is going to be chords of 0 and chords of 1. Now, what can we say? If the current coordinate x comma y is in visit, then obviously there's no point in doing anything else with it, so just continue. Don't do anything else. Otherwise, if we make it past, that means that we have not visited yet. So let's add it to visit, like so. And now we need to have the basic case of if x comma y is equal to the final destination. And what is the final destination? Well, we have lane heights rows, and our columns is lane of heights 0. So the bottom rightmost position is going to be rows -1, comma calls -1. So if this is the case, then we've reached our destination, and we should just return the effort it took to get to this position, because the heap is going to always give us the minimum. Like when we pop the uppermost element, it's always going to be the path with the least effort. So up to that node. So basically just return the effort here. Otherwise, we can just get to a new node. So for dx dy in 1 0, 0 1, -1 0, and 0 -1. So basically get us to a new node from the current node. The new coords nx and ny is going to be the current x plus dx and the current y plus dy. So this is just a very quick way to get to a new node, and in the four like vertically and horizontally adjacent neighbors. So we need to check if nx is less than 0, or nx is greater than or equal to rows, or ny is less than 0, or ny is greater than or equal to calls, or nx comma ny is in visit. It means that this is not a valid coordinate. We should not consider it. So just continue. Otherwise, we can do stuff with it. So we're going to travel, for example, to 2 now from 1. How do we push it? Well, we have to now know the new effort, right? The new effort it's going to take is going to be the maximum effort, right, that it took to get to the current node with the effort it takes to get to the new node. And the effort it takes is the absolute difference between the new node, which is nx and y, right, minus the current effort. Minus the current position that we're at, right? It's the difference between nodes. So it's going to be x comma y, like so. And then we can just heap q dot heap push into our heap. And what do we push? We are going to push we're going to push a tuple, and the first element is the effort. The second element is nx comma ny. So with that, this is guaranteed to return at some point because BFS is going to traverse everything. So that should be the entire code. So we can now just run it and see what happens. And it works, so let's submit. And there we go. That's the solution.